Let us start. Today we are doing the last problem of our discussion about the vapor compression refrigeration system. Here in this problem, what is given is a food storage. It has a refrigeration capacity around 12 metric ton and works between the temperature, evaporating temperature of -8 degrees centigrade and condensing temperature of 30 degrees centigrade. So T1 equal to T4 equal to -8 degrees centigrade and T3 is equal to T4 is equal to T3 is equal to T2 is equal to 30 degrees centigrade. The refrigerant used is R12. It is subcooled, means 5 degrees centigrade, which it is cooled at wet saturation, wet saturation condition up to 5 degrees centigrade before it comes out from the condenser and goes into the expansion valve, and the vapor superheated to -2 degrees centigrade before leaving the evaporator coils itself. So the evaporating temperature was -8 degrees centigrade, but the temperature superheated to -2 degrees, -8 degrees centigrade, 8 degrees centigrade, but temperature superheated to -2 degrees centigrade before it goes into the leaves in the evaporator coils and goes into the compressor coils, compressor cylinder. Now there we have two cylinder, single acting compressor operating at 1000 RPM with stroke equal to 1.5 to 5 the bore. So the diameter, the relation between the diameter is given and length, the stroke length is given, but none of them is given, so that we have to calculate them. So determine what the COP, theoretical power, part turn of refrigeration required, and bore and stroke of the compressor when there is no clearance and there is a clearance of 2% itself. Now, what to do? What is available here is given as per the saturation temperature, which is lower than T1 is equal to T4, and as for the evaporating process, the low pressure, which is also constant, which is given as 2.354 bar, and for condensing process, which is doing at isothermal, which is rejecting heat at isothermal process at temperature 30 degrees centigrade and at constant pressure at 7.4551 bar itself. The enthalpy given, so what is given here, the tonnage is 12 metric ton, means 12 multiplied by 210 kilojoule per minute is the power being absorbed in the compressor itself, in the compressor during the compression itself. T1 is the temperature. Here you see there are T1 dash is my T1 dash and T1. There are two temperatures there. T1 dash is the temperature at the evaporator, right on the vapor refrigeration cycle, vapor saturated vapor line, and one is the temperature which is in the superheated region, but it is higher than the 1 dash, means it is with higher temperature than 1. And T1 dash is given is the lot is that evaporating temperature at -8 degrees centigrade, which is equal to 265 degree Kelvin, which put here as 265 degree Kelvin itself. Next, T2 dash, it is the temperature of the superheated of the dry saturated vapor over the saturated vapor line after it comes out and from the compressor and enters into the condenser itself, where it is cooled from T2 to T2 dash and reaches dry saturated line, where it is cooled the refrigerated isothermally from T2 dash to T3 dash, and then it is cooled the refrigerant from T3 dash to T3. So here T2 dash is given as 30 degrees centigrade, which is equal to 30 plus 273 degree is equal to 303 Kelvin itself. Now T3 dash minus T2, but degree as proportional is given as 5 degrees centigrade itself. Means this is there is a reduction of 303 to 298, means 5 degree temperature reduction at between the supercooling process itself.
Hello, sir.
Ah,
Sir,
follow.
sir, I have some network issue, sir.
Yeah,
Sir, network issue हो रहा है सर मेरे को.
your network is not working.
Yes, sir.
Okay.
I have no network, sir.
No. Where you are, you, change your position to a certain extent. You are doing it in
Okay.
mobile,
Yes, sir.
but try to change your position. I hope that you will get it. Network issues
Okay, sir.
everywhere.
Yes, sir.
Take care. Try to change your
Yes,
position to a certain extent and then try to join and go to
Okay.
concentrate in the class. Okay. Now that is the yes. Next, there is the subcooling is done by 5 degrees. So here T3 to T3 dash. Here T3 T3 to T3 dash difference is only 5 degrees. So T3 is 298 and T3 dash is 303 degree Kelvin itself. Next, T1, which the as the as it is stated in the problem that the refrigerant is entering into compression in superheated region. So it is clear that the point of entrance of the refrigerant is not on the dry saturated vapor line, but in the superheated region. And the temperature of the superheat is given as -2 degrees centigrade, which means that this is 271 degrees centigrade Kelvin itself. Now, in the problem, what is given? The HF1 means 28.5 degree, 28.2 degree Kelvin, which temperature at the dry saturated level, which is actually HF1 dash. With the temperature at this level, which is for more or less coming from this thing, when what is the enthalpy of the liquid refrigerant at temperature T1, at temperature T1 to T1 or T4, T1 dash is equal to T4. So here it is 28.72 degree Kelvin itself. And T3 dash, the temperature of the enthalpy at the liquid state at temperature T3, at T3 dash, which is given here, which is the liquid enthalpy at temperature equal to 62.59 degree Kelvin itself. H1 double dash, H1 dash, just 1 second. H1 dash, H1 dash is the enthalpy at superheated region, that is at the point of entrance is 187.07, means here. And here it is using the problem is being used the enthalpy at H1 dash as well as H1 itself. Yes, at enthalpy at the vapor stage at -8 degrees centigrade, 8 degrees centigrade itself. And H3, actually this is also H1 itself. This is actually H1. It is written here as H1 itself. And H2 dash is the enthalpy at the point 2. It is the enthalpy at the superheated state at temperature T2 dash or T3 dash, that is 303, which is equal to 184.07 itself. And T2 dash temperature at the I'm sorry, this is the T2 dash is 199, the temperature of the vapor stage here, and T3 dash and H3 dash is equal to 64.9 degrees Kelvin itself. That is 64.9 degree Kelvin itself. That dry saturated. H2 H22 dash is this. H2 is enthalpy at here, it is given as 199.62 degree Kelvin, right? I was getting confused. Now, the entropy, so let us come to the entropy. Entropy of the fluid at point 1 means entropy at the temperature 1 itself is given as 0.11, 0.1149 degree Kelvin itself. Here, entropy at the point 1 is showing that enthalpy and entropy at point 1, but it is superheated stated. It's not given in the chart, but it's given as entropy or entropy at superheated state itself. So here, 1149 kilojoule per kg is the entropy itself at point 1, and which is in the fluid state is somewhere here, and entropy at the fluid state at point 3 is given as 0.24, which is 30 degrees centigrade. It is the entropy at the fluid state at start 3, and S1 dash is the entropy at vapor state is equal to at the point 1 is equal to 0.707007, and S2 dash entropy at of the refrigerant at vapor state at the point 2 dash, which is given as 0.6853, and V1 and V2 is the specific volume given here. Is the specific volume of the refrigerant at temperature T3, means when it is at the evaporating state, in on the vaporized particle evaporating state, and at 30 degrees centigrade when it is at the vaporized in the condensing state itself. And CPV, specific heat of liquid refrigerant is given as 1.235, and that is a refrigerant is equal to 0.733. So specific heat of the vapor refrigerant at will be here at the point 1 to 1 dash when it is the vapor stage, and 2 to 2 dash, and is given as 0.733. And when it is liquid between 1 to 1 dash and 3 to 3 dash, etc., when it is given as 1.235 kilojoule per second. So here the refrigerant is the liquid in the liquid state, and here refrigerant is the vapor state. So here you have to use this type of this effective values of the enthalpy itself when you have to do. Now we have to suppose to calculate the entropy at the point 1 itself. Entropy at the point 1 S1 is equal to given as S1 dash plus 2.3 into specific heat of the vapor refrigerant multiplied by log of T1 dash, which is at the lower temperature, to T1 divided by T1 dash, means T1 is the higher temperature and T2 is the higher temperature. So entropy rise from this formula, which is available by putting the respective values of S1 dash and S1 dash CPV, and 271, T1 is equal to 271 and T1 dash is equal to 265. Now, thus, if we after putting this value and after simplification, we get S1, its entropy at the point 2, at the point 1 is equal to 0.7171. It's a kilojoule per kg degree Kelvin itself. Next, S2. S1, S2 is given as S2 dash plus 2.03 CPV, means specific heat of the vapor refrigerant log T2 divided by T2 dash, means T2 is the higher temperature of the superheated vapor, and T2 dash is the temperature of the refrigerant at dry saturated state at high temperature instead. So we know the value of T2 dash, but we don't know the value of T2. We know the value of CPV, and we do not know the value of S2 dash and S2. S2 is equal to S1 itself. So put the values of respective values, 0.6859 plus 2.3, 0.733 log T2 divided by T303 itself. Because T2 dash temperature at here, it is 303. So put the value, then put it equal to the entropy at the point 1, that is just calculated is equal to 0.7171. So we put the value of this equation equal to 0.7171, and so here we are getting the unknown value only T2, or after simplification and making the necessary taking under anti-log, we'll get T2 by T is 1.00444, or T2 is 1.044 is equal to 303, 3.16.4 degree Kelvin. So we have got the temperature at here, and we have got the entropy at here. Now we know we have to calculate the enthalpy at point 1. That is H1. We have to calculate here. H1 is given here. H1 dash, the enthalpy at the point 1 dash on the vapor saturated line, which is given in the problem, plus the specific heat of the vapor refrigerant multiplied by the rising temperature from T1 to T1 dash. We have calculated, we know the values of T1 as 271, we know the value of T1 dash as 265, and know the specific heat of vapor as 0.733, all three are given, and the enthalpy at the point 1 dash means enthalpy of the vapor refrigerant on the vapor saturated vapor line is given as 184.07. So putting the respective value and calculating, we get H1, the enthalpy at the entrance of the compressor is equal to 188.47 kilojoule per kg. And next, let us go for H2 dash, H2, which is given as H2 dash plus the specific heat of vapor, specific heat of refrigerant vapor multiplied by the rise in falling temperature from H2 T2 to T2 dash. So this is given as H2 dash plus CPV plus T2 dash, T2 minus T2 dash itself. So H2 dash is available from the chart, which is given as the enthalpy of the vapor at the higher temperature, the condensation temperature, which is 199.62, and CPV is given as enthalpy of the vapor refrigerant as 0.733 and multiplied by 616 T2, temperature of T2 in degree Kelvin, minus 303, which is calculated as T2 dash. So by putting all these values and made after the calculation, we get the value of enthalpy at the point 2, or at outlet of the compressor is given as 2.209 per 4 kilojoule per kg. The enthalpy at inlet, enthalpy at inlet, enthalpy at outlet of compression. Next, enthalpy of liquid refrigerant at point 3. How will you get it? We know enthalpy at liquid refrigerant point 3 will be equal to enthalpy at the liquid refrigerant at point 3 dash, which is known to us, which is the enthalpy of the liquid refrigerant on condensation temperature, which is given as SF3 is equal to 64.59 minus the specific heat of the liquid refrigerant, which is given as 1.235 multiplied by the falling temperature from T3 dash to T3. So this is only 5 degree. So this is after putting this value, it gets HF3 is the 58.42 kilojoule per kg, which is the entering temperature at the enthalpy at the entrance of the enthalpy at entrance of the expander. Now, so we know as per our definition of coefficient of performance, or performance is the refrigerating effect, which is expressed in this system, H1 minus HF3. H1 is the outlet temperature of the refrigerator, outlet enthalpy of the evaporator, and HF3 is the inlet enthalpy of the evaporator divided by the H2, means enthalpy at the outlet of the compressor, and divided minus at H1 enthalpy at the inlet of the compressor. So This is the amount of work is put in the system, and this is the amount of refrigerant effect we are getting. By putting the respective values and calculating, we get the COP is equal to 6.2. Now, we have to calculate the theoretical power per ton of refrigeration. Now, whether the heat extract or refrigerating effect per ton of the refrigerant is given as RE. H1 minus HA3, we have calculated both H1 and HA3 itself. That is equal to 130.003 kilojoule per kg. And refrigerated capacity of the system is given as 12 metric ton. This 12 will multiply by 210 to 2520 kilojoule per minute. So this amount of refrigeration we have to calculate, you have to create, and by sending that the equivalent amount of by using the equivalent amount of refrigerant throughout the system, and which will be given by the value by the ratio the refrigerating capacity by but divided by refrigerant effect created per kg of the refrigerant, which will give us by division will get the mass flow the refrigerant throughout the system in kg per minute, which is 19.4 kg per minute. Now, work done during the compression of the refrigerant is thus with mass flow multiplied by the enthalpy rise, mass flow multiplied by H2, which is calculated is equal to 209.44 minus 1.8H1 calculated as 1.88.47 and equal to 406.82 kilojoule per minute. That's why the theoretical power, this is the power required by the compressor per minute. So theoretical power is given as this is divided by power given per part second, which is divided by 60 multiplied by 60. This is a kilojoule per second divided by 12. This is the actual power and differential power. Yes, we have 12 tons of refrigerant capacity, 12 tons of refrigerating capacity. So theoretical part ton power per required part ton of refrigeration is given by 3406.42 divided by 60 means kilojoule per second divided by part ton means that per 12 ton, if we divide by 12, we'll get part ton of refrigerating power required. And theoretical power required per ton is 0.565 kilowatt per second, kilowatt per ton itself. Now, what will be the bore and stroke of the compressor itself? Now, what should be the now let us go for next question of the problem, the bore and stroke of the compressor itself. Let us say, assume G is the bore of the compressor, L is the length of the compressor, and which is given as 1.5 D, but especially N and D and L is not given, which is supposed to calculate, and speed of the compressor is given as 1000 RPM. These are all given. Now, from the universal gas equation, or universal gas equation, equation P1 V1 by T1 is equal to P2 V2 by T2, where V1 by T1, V1 dash by T1 dash, because P is same for the compression process. Now, the specific volume of the suction, that specific volume of the suction of the compression at point, let us have V1 by V1 dash is equal to V1 dash by T1 dash. No, it's not applicable here. No. Let us first find out the specific volume of suction of the compressor, that at the point 1 or at the point of entrance of the compressor itself. So if we apply Charles law, that is V1 by T1 is V1 dash by T1 dash. Here at the point of temperature, ratio of volume to temperature is equal to ratio initial or final, initial volume and final volume, and initial temperature and final temperature, more or less they are same. Now T1 at the time of V1 is the volume at at the dry saturated pressure, and V1 is the volume, specific volume V1 dash at superheated state at entrance of compression, and V1 itself is the, there we have a dash, V1 is the specific volume at in the dry saturated vapor of the compressor itself. Dry saturated volume at of vapor inlet. Temperature is the temperature of the refrigerant in the vapor stage on the dry saturated vapor line, and temperature T1 dash is the temperature at superheated superheated refrigerant at the point of entrance here. Here the specific volume is changing from V1 to V1 dash as the temperature is increasing from dry saturated to superheated. Temperature is increasing from T1 to T1 dash of the liquid vapor refrigerant as it is increasing from T1 to T1 dash itself. So if we got what will be the specific volume of V, and specific volume at V1 is given, that is 0.97990 multiplied by T1 dash. T1 is given and T1 dash is also given, is equal to 0.81. So the specific volume of the vapor at the moment of point of theoretical entrance is given as 0.81 cubic meter per kg. That's something. Let us see the specific volume vapor minus 8 actually output minus 8 to the centimeter per 0.79 is column. V1 is the specific volume of superheated vapor at entrance of the superheated vapor entrance made of full liquid. That is superheated vapor at the entrance of the compressor, that is V1, and V1 dash specific vapor at the saturated vapor at the evaporator itself. As we know the value of V, and we can So you know the value of P1. It is the specific volume of the liquid refrigerant. I mean vapor refrigerant at the at minus 80 degree temperature, and P1 we don't know what is the specific volume at the entrance of the refrigerator entrance of the at the compressor where it is in the superheated state itself. So temperatures are known, and the dry saturated temperature is known, and superheated temperature is calculated. So if we put all of them, we know the volume of the specific volume of the flow volume of the refrigerant at the entrance of the compressor itself. When there is no clearance, so the theoretical suction volume of the piston is equal to the theoretical suction of piston volume per minute will be equal to mass flow of the refrigerant multiplied the specific volume. So mass flow is calculated multiplied the specific volume at the entrance of the compressor is given as 1.57 cubic meter per minute. So the theoretical suction volume of piston displacement per cylinder per minute would be, there is two cylinders are there in the compressor. So we put it 1.57 divided by 2 is equal to 0.785 cubic meter per minute. But that is the theoretical suction volume of piston displacement. Then theoretical suction volume or piston displacement per minute is the piston area multiplied by the stroke length multiplied by the RPM of the compressor itself. We know the piston, we don't know the diameter and length, but we know the relation between them. So we put the cross-sectional area of the piston as pi by 4 into d square multiplied by d square multiplied by length particularly n, and pi by 4 into d square multiplied by 1.5 d, whereas stroke length is equal to 1.5 times of d, and the n RPM of the piston is 1000 RPM. So if we make the calculation, we get 1178.25 d cubic meter per minute is the theoretical suction volume. If we equate them together, what will happen? Theoretical suction volume is equal to the 0.785 cubic meter per minute. Thus, d cube is equal to 0.785 into 11.7825 divided by 0.78 divided by 1178.25 is equal to 0.000666 millimeter itself. And this is d cube, and d will be 0.87 meter or 87 millimeter itself, and length will be equal to 1.5 d into 1.5 to 87 into 130.5 millimeter itself. Now, if there is a clearance is given as 2%, so d2 will be the specific volume at 0.2, and c is the clearance given as 2% or 0.02. So applying Charles' law to 0.2 and 0.2 dash, which is where 0.2 is the volume at specific volume at the 0.2, which is the inside the condenser, which is shown. 0.2 at the outlet and 0.2 dash at the condenser itself.
Sim, sapatos que ali é que os bodegos desse do minha guma. Foi na do colégio.
Now, no, I get this started. Now, the specific volume is between the 0.2 means at the exit of the compressor, at the refrigerant at the exit of the compression, and 2 dash refrigerant value of the refrigerant, which is on the dry saturated vapor line and inside the condenser itself. So V2 and V2 and T2, and we know T2 and T2 dash, and V2 is the temperature at the outlet of the refrigerant itself, but we know the V2 dash, which is on the which is the specific volume of the entropy at the condenser at the height at the temperature T3, which is given here. With a specific volume of the dry saturated vapor at condenser temperature at 30 degree, which is given at which is equal to V2 dash, and this is equal to V1 dash itself. So as V2 dash is given, so V2 dash is given, so V2 or the specific volume at the outlet of the condenser, it can be calculated easily. That is equal to 0.235 265.34 is equal to 2.024 cubic meter per second. Now, what will be the volumetric efficiency of the compression? Means the amount of the volume of the refrigerant which is actually delivered in comparison to the theoretical volume, which I've already calculated, is given by this equation. Volumetric efficiency 1 plus C means the clearance minus C V1 by V2. So we know the V1 and we know just we have calculated V2, and we have already calculated V1. We put them, we know point the specific your clearance, that is equal to C 0.02, and so the volumetric efficiency will be calculation 0.954. Hello.
सर यस सर ये चार्ज लो जो है 2 and 2.5 का वो कैसे गया सर? Yes sir.
What we are doing here?
Yes sir.
We are applying Charles law here and here. Why? Because we know the specific volume of the refrigerant here. We know the specific volume of the refrigerant here, but we don't know the specific volume of the refrigerant at entrance and that at exit. Okay, we are applying Charles law between this for vapor and this for liquid. So you are getting V1 and we are getting V2. V1 is the specific volume at entrance and V2 is the specific volume of exit. So if we put them equator, you know what will be the efficient volumetric efficiency itself, and you know the clearance itself, which is given. So from this equation, which I taught to at the time of reciprocating compression, here we are getting, we know we have put the value of V1 and V2. V1 at specific volume at entrance of the compressor, V2 specific volume at the exit of the compressor. C is the clearance volume, clearance given in the compressor, which is already given, that is 2%, 0.002, and 1 plus 3 minus C, V1 plus V2. So with this equation, we get the volumetric efficiency 0.95, 0.95 or 95%. So pressure displacement will be mass flow of the refrigerant multiplied by the volume coming in divided by 2 is the number of cylinders. Then divided by 1, the efficiency is 0.95. The piston displacement in the inside will be given as 0.8325 is there. Again, we are equating that equation, which is means pi by 4 d square into L as a solid volume. This is equal to 1.5, etc. 1.5 d. So 1178.25 d cube is equal to 0.8236. If we make that is d cube is equal to 0.00070, make the cube root, that is 0.0887 meter or 88.7 millimeter, or length 1.5 into length is 1.5 into 88.7 is equal to 133 millimeter. So if we compare, if there is no clearance that is the diameter will be 87, and if there is a clearance of certain percent, that diameter is supposed to be increased to 88.7, and accordingly length is also changes. Length is increasing here, and length is more or less less here. If there is 100% efficient, so which means that if the compressor is 100% efficient, then the diameter length requirement is comparatively less. If there is some, then the position where there is some efficiency is greater. So with this, we have completed the vapor compression refrigeration. Vapor that is vapor compression refrigeration system. Refrigeration system. Cycle. What we have done first, we have made a TS diagram, TS, and a pH diagram, that is pH. This is available. This is pH chart. This is here. This is pH chart itself. What we are doing here, initially what we have done, one, two, three, four. Here, 1 to 2 is the compression line, compressor. Shows the compressor process or compression process. 2 to 3 is the condensing process. 3 to 4 showing the throttling or expansion process. And 4 to 1 is the evaporating process itself. What we are doing, we are using a refrigerant. Which is in liquid state in some portion of the cycle, and in vapor state some portion of the cycle, and we are using its latent heat of vaporization and latent heat of condensation for extracting the heat inside our refrigerating chamber, which is housing the refrigerating coils surrounding it. And by subtracting the latent heat of vaporization from this chamber, we are cooling the refrigerant chamber itself. Next, we are just by absorbing the heat and converting the liquid refrigerant to gaseous. Then we are sending to compressor. Compressor is compressed from 2 to 1. Then and vapor refrigerant at high pressure, then sent to condenser, where it is condensed and becomes liquid at high pressure and temperature itself. And then it is sent to expander, where it is expanded and its pressure is reduced to temperature 4, and then again sent to evaporator itself. We have done different cases like this. Say we have assumed always our position was to improve the COP, which is the refrigerating effect, means amount of refrigerating effect divided by the compression work. We have to improve it, because for the same amount of compression work, how much refrigerant effect we are created. So we are having different type of the process, like say subcooling. Oh, this is finished.